Okay, so we're starting now. Okay, so I guess I need to do the introduction again.
Sorry.
That's okay, I forgot to press the button. Good afternoon, everyone, and welcome to today's webinar on motor protection theory and the GE Multilink 869 motor protection relay setup. My name is Eduardo Iglesias, and I'm the Senior Regional Manager for the industrial market in the Southeast US. And on behalf of the grid automation team supporting this event today, I would like to thank you for taking time to participate in the session. Let me take a minute to go over some of the housekeeping items. This session is being recorded, and as such, you will have access to the video for the next 90 calendar days using the same link that you used today in order to get to this webinar. The session is muted, so if you want to ask a question, please use the chat box. That's the one that has the question mark on it, and we'll be answering those as they come in. We will email you a copy of the presentation, and if you need your participation certificate, please email me and we'll make sure that you get it within the next 24, 48 hours. With that said, today we have two of our senior technical application engineers, Paul Smith and Christine Kreitz, which will be conducting the session. Paul, if you may.
Very good. Thank you, Eduardo. Right, so today I am going to talk about motor protection fundamentals, and then we will touch on the 869 relay and some of its features later on, and then also look at the software that you use to configure the relay. But most of the first part here is generic motor protection information, and first we're going to talk about motor theory. So the motor has its main parts. It has a shaft as well as a stator and a rotor. The shaft is what connects to your whatever it is you want to move. The stator stays still and the rotor rotates. It does this by setting up a the stator sets up a rotating field. You can see the windings in this drawing here, these drawings here, and you can see that in this this particular diagram that it's a two-pole machine, so each phase has two poles. The winding pairs are 120 degrees apart, and again, that rotating magnetic field, when AC current and voltage are applied, is what then turns around and drives the rotor. And here's a little schematic for that. The opposite magnetic polarity on each pole is then rotates through the coils, and again that drives the rotor to turn. And this is showing the vector force being the result of combined magnetic fields. So it pushes that rotor. The stator field of a two-pole motor rotates at 3,600 RPM. It's the synchronous speed of the motor. As you increase the number of poles in a motor, the synchronous speed decreases. You can see the table there. So you can calculate that synchronous speed based on the number of poles, or you can work that backwards and figure out the number of poles based on the rated synchronous speed. So the rotor has conductor bars, steel laminations, and then it has a shaft. It is made up to look like a conductor that cuts through that magnetic field. Now you've heard it called a squirrel cage because it has this cage that it's built into. So physically this is what it looks like, but electrically it's just this loop that cuts through that magnetic field, and then the torque is produced from the attraction and repulsion between the stator field and the rotor bars. It's important to note that the rotor and the stator fields never match in speed. So even though that the speeds we looked at before were the speed of the field, the rotor actually never catches up to that, and we call that slip. The difference in the rotor speed versus the stator speed is the slip. And here in this example, we've got a stator field speed of 3,600 RPM, but the rotor speed is 3,510 RPM. That's a slip of 2.5%. And slip increases as you load your motor. So next I want to talk about what can go wrong with motors. And we're going to talk about motor electrical failure modes first. And I'm going to go ahead and pop in all of these little pictures. Okay, so there are all kinds of things that can go wrong with the motor electrically. All of these look like, or most of these look like some sort of a fault, whether it's a inner turn insulation fault or a stator inner turn fault, where a stator ground failure, where parts of those windings either connect to other parts of the windings or connect to ground. It's really just the current not going where it's supposed to due to insulation problems. We also have some other types of electrical failures that we look for. Over/under frequency, power factor are a couple of those. Unbalanced current. Each of these, over/under frequency, unbalanced current, they create they can create extra heat in the motor, and that's why electrically we want to protect for that. The other thing that we look at can also be loss of load process, or loss of load or process. If whatever the mechanical element is that you're driving, whether it's a fan or a pump, if it loses whatever it is that it's providing that drive to, then you may want to trip off your motor and examine your process. The other type of failure mode I'm going to talk about today is the thermal stress, thermal failure modes, and these are important because what we're protecting here is overheating the motor, and heat in your motor is not your friend. It contributes to a shorter life for your motor. It's just so it's one of the things that's important to protect for. And we do this by looking at, we have a thermal model for the motor, and it will take into account things like extreme starting conditions, high ambient temperatures, if you lose your forced cooling, single phasing, harmonics, and unbalanced current. Again, they can produce extra heating in your motor. Also an increase in load if your process overloads your motor, that can cause heating. And then locked rotor conditions will also cause that, equivalent to a starting current, running continuously. All these things overheat the motor and can lead to a breakdown in insulation. There are other things that we protect for in relaying, specifically now some mechanical type of failures, and those we're going to cover in 2 weeks in a separate session. Christine Kreitz is going to cover that in 2 weeks about the same time. So today I'm talking about the electrical and the thermal protection. So for motor electrical protection, we're looking at thermal overload, process caused, from excessive load, high ambient conditions, hot or blocked ventilation, power supply issues with voltage or current, unbalanced harmonics, phase faults, ground faults, as well as abnormal operating conditions, over voltage, under voltage, under frequency, voltage and current, load loss, jamming, and jogging. Jogging your motor, starting it too many times in a row, can cause additional heating. So a little bit more on why overheating your motor is a problem is that the stator windings and the stator winding insulation will degrade for high temperatures. So if it says your insulation lifetime decreases by half if the temperature exceeds the thermal limit by 10 degrees C. So this has some example here of for a let's see, the example here is an F class insulation. The stator temperature of 165 degrees decreases motor lifetime by 50%. So because your F class is 155 degrees, just that 10 degrees is going to decrease your expected life of the motor by 50%, expected life of the insulation. And then also you have the possibility of rotor conductors deforming or melting if your thermal limit is defined by the motor stall time. So let's talk about this overload protection and the thermal model. The thermal model tracks motor heating for both the stator and the rotor. The main parts of the model are the overload pickup level, the overload curve, the running and stopped cooling time constants, the hot-cold stall time ratio, RTD and unbalanced biasing, and the motor state machine. The typical motor has 4 states. It's either stopped, it's starting, it's running, or it's overloaded. The stopped state is when your current is less than 0 and your contactor or your breaker is showing you an open status. Starting is if your previous state was stopped and now your current goes above 0. Your motor current must increase to a level greater than the overload pickup within seconds. Otherwise, the motor algorithm declares running. But running is if the previous state was starting or overloaded and the current drops below overload pickup level. So when you're starting a typical motor, your current goes up to 5-6 times full load current, and then drops down rather quickly. So that's that part is the starting part. When it drops below that full load amps, it becomes the state of running, and then finally, if you're running and the current rises above the overload pickup level, it's overloaded, and that is when the thermal capacity used begins to accumulate. So the motor thermal limit curves, and these come from the manufacturer. They've designed the motors, to run at particular loads. So so you have a running overload and a locked rotor overload, which is your starting curve. And you want to match the curve to the thermal damage curve. You match the curve of your relay to the thermal damage curve from the motor manufacturer. We have standard curves, and you can adjust those. You can adjust those, or you can construct customized curves. Let me just step you through this drawing here real quick. So this A curve here is the cold running overload, and then B is the hot running overload. The hot curve takes into account that the motor is already heated up, so it's a little faster curve. C, the cold lock rotor curve, and D, the hot lock rotor curves. These are the limits if you have a locked rotor, which is out here at 5 times your rated current for too long, it will cause a trip there. And then the E and F, these curves down here towards the bottom, these are your acceleration curves. The acceleration at 100% voltage is this F, which is fine and good, but you need to also keep in mind that there's a slightly different curve if the voltage drops. This is at 80% voltage, and you can expect to have a voltage drop when the motor is first starting. Again, most of this information comes from the manufacturer. For example, the curve I showed you, and this is showing some of the data that we pick up off of the manufacturer's data sheet. The service factor is set to the maximum allowed by the motor manufacturer. It's set slightly above the motor service factor by 8 to 10% to account for measurement errors. If RTD biasing is used, thermal overload setting can be set higher, but your maximum overload is 125%, and this is to the limit of your motor feeder cable. So no matter what what sort of service factor your motor has, we don't set it any higher than 25% because the cables can only handle that amount of current. So we'll talk a little bit more about thermal capacity and the thermal capacity used concept. But the thermal capacity represents the motor thermal condition. The TCU, the thermal capacity used, is percentage of motor thermal limit used during motor operation. A running motor has some level of TCU because of motor losses, and the thermal trip the thermal trip operates when the TCU equals 100%. And the picture here is showing that there's a certain amount of ambient temperature in the motor. There is unbalanced current that adds to the thermal capacity used. Motor losses will add to that, and all of that is thermal energy that is built up in the motor. And you can consider as the motor starts and these various losses and problems occur, the thermal capacity gets used. As the motor runs, then there's a certain amount of cooling, and this thermal capacity used will come down and hit some sort of equilibrium. So selecting the thermal overload curve. The overload curve has to be set below the cold thermal limit, but it can be set above the hot thermal limit. If you only have the hot curve provided by the manufacturer, then it has to be set below that. So we have the cold curve and the hot curve, and what we want is to have our protection thermal overload curve to fit right in there, and so we have picked one that fits right there. There's your example. If you only had the hot curve, then you would have to set it below that. And the standard motor overload curves are in the manual. They're probably available other ways, but it maybe doesn't look like it, but this curve here is on a semi-log scale where your rated current is your straight units here, but this is on a log scale going up. But if you look at this, your motor curves or the relay curves, they are set up on a log scale. So it looks a little different, but this is the same curve. And we can adjust we adjust this curve by adjusting the multiplier. So there's a ×1 multiplier up to a ×15. And you can adjust that in the relay settings. So that has the effect of moving this curve up and down. And then the curve is set up here based on a multiple of full load amps. So one is always your pickup, and then the curve goes out from there. But in order to move this on your actual motor overload curve, you can adjust the pickup to shift this left or right. So the pickup shifts it left or right. The multiplier shifts it up and down. So that's how you move that curve where you need it. The hot-cold stall time ratio, or the HCR. Again, this is provided from the manufacturer, although they may call it, may have to derive it from some of the other settings. So the motor manufacturer provides the locked rotor thermal limits. So you've got a cold motor at ambient temperature, and then you can have a hot motor at rated temperature for a specific class and service factor. So these are the locked rotor thermal limits. The thermal capacity used rises and falls based on an average current and the HCR. And relays employ this HCR to calculate TCU at which the motor settles for current below overload pickup. So the NEMA standard temperature rises for motors to 1,500 horsepower and service factors 1 and 1.5 respectively. This shows the maximum operating temperature and allowable rise for those different classes. But to determine the hot-cold safe stall ratio from the data sheet or the HCR, what you're going to look at is the locked rotor time hot and the locked rotor time cold, and that is what usually shows up on your data sheet. So here it's 35 seconds cold, 30 seconds hot, so that's 30 divided by 35, or 0.86, would be the setting that you put into the relay. If the manufacturer doesn't present those figures as numbers, you can get those off of the thermal limit curves. If you look at the vertical line here that intersects the hot and cold curves at the stall point or the locked rotor current, you'll see that you can determine the times of those two intersections. So on this example, we have a locked rotor times hot and cold of 6 seconds and 8 seconds. So that measures across to here. So the ratio there is 0.75. If the hot and cold times are not provided, then you assume your HCR is 1.0. That's your worst case, and the relay will just calculate from that. I mentioned that we have the ability to create custom overload curves. And this might be if you have a motor starting that infringes on the thermal damage curve. For example, here you can see, all right, here's your running curve. Number 3 is your acceleration curve. If you try to get a curve right in here, it's going to hit these motor starting curves here. So it's difficult sometimes to get a curve that works, specifically on these high inertia loads where the acceleration time can exceed the safe stall time. So what we can do is create a custom overload curve that fits right in here. It will even have this little notched area if you want it, and that can be programmed into the relay. We also have the capability to set a voltage-dependent dynamic thermal limit curve. This is again for high inertia start that's longer than your allowed safe stall time. It accounts for the current change during acceleration. So when you're first starting your motor, this is showing a 20% voltage drop, or it drops to 80%. So your limits are here, shown by this darker black line. But if you but as the motor and the load start to rotate, the voltage will recover, and for that then you can get a different curve and so the relay will shift this curve from here to here and allow you to start your motor. And here is it's a kind of another picture. This shows the shift, but also shows what this is an example maybe to take with you that shows how these set points are determined. Yeah, that looks like the same slide, doesn't it? Okay. So moving on now, a different part of the thermal model. Like I said earlier, the current unbalance will cause heating in your motor. So we bias that thermal model based on unbalanced current, negative sequence currents, or unbalanced phase currents, or how we measure that additional rotor heating. Causes of this current unbalance can be a single phase blown fuse, loose connections, stator turn-to-turn faults, system voltage distortion and unbalance, or just specific faults in the system. So so what we do is we use this formula here that takes into account the current imbalance. And like I said, this is your actual motor current. Well, IEQ is your equivalent current. Takes the actual motor current, factors in the negative sequence current and the positive sequence current, and uses that to come up with this equivalent current, and that's what the model uses to show to end up with the calculation for the thermal model. There are NEMA ratings for based on voltage unbalance. When K equals 8, the derating in the motor is identical to a NEMA recommended derating curve. So with the K value in the relay is typically configurable, and here you can see the curves that relate to the different K values. But right, so but in a K setting of 8 matches the NEMA recommendation, but you can use a typical value or a conservative value based on this multiplier divided by the locked rotor current squared. So a little bit of flexibility there in the setting of the relay, but it's all to derate your motor or add to that thermal capacity based on voltage imbalance. Another option that we have in the thermal model is to use our RTDs. Our RTDs measure temperature from your stator windings, and the temperature then is used to bias the thermal capacity used based on that temperature. It can accelerate the thermal trip for hot stator windings. It is separate from the overload model. So just because your thermal capacity is at 100% does not mean that the relay will trip unless you set it that way. It won't trip for overload. Got to keep that in mind. The overload and the thermal capacity are two different things. The relay uses the calculated thermal capacity unless the RTD thermal capacity is larger. It trips at maximum temperature only if the average current is greater than the overload pickup setting. So it's got to be in an overload condition to use that thermal model as a reason to trip. This is backup protection for loss of cooling and unusually high ambient temperature. So the way this works is you enter in values here for this this RTD bias minimum, this RTD bias center point, and this RTD bias maximum. And let's see, in this example, the insulation rating is 155. That's your maximum. The rated temperature is 130. That's your center point. And then your minimum is your ambient temperature. So these are coming from your motor ratings. So your running cool time, when your motor current is less than overload pickup, the motor cooling rate is equal to your thermal capacity used, and it's in this. I guess what I don't want to you guys to fall asleep because I put a formula up here. So just to sort of show you what's going on, this this is showing an exponential factor based on time and that cooling rate, and this is just using the thermal capacity used at the start, thermal capacity used at the end, and that gives you this formula that we use, that the relay uses internal. So maybe this will help a little bit. The cooling time constants for running and for stopped are different. Typical ratio of a stopped to running cooling time constant is 2 to 1. So in this example, when the motor is tripped, it is stopped from a fault, the cooling time constant 30 minutes. The cooling looks like this. It takes up to well, motors cool in 5 time constants. So if your cooling time constant stopped is 30 minutes, then it's going to take up to the 150 minutes, right? 5 times 30, 150 minutes to cool down to 0. When the motor is running, the cool time constant, again, it's typically 2 to 1. So here it's 15 minutes. It takes five cooling time constants to cool, but in this case, it's going to cool down to an equilibrium value. And so after 5 times 15, I don't know, not really good with numbers, but was that 90 minutes? So it's going to take 90 minutes then to reach this equilibrium point, and this equilibrium point here is not 0. It's something a little more than 0 because there is, heating that goes on in the motor while it's running. So the thermal capacity at 80% motor rated current, we get that again based on the I equivalent. I showed you that calculation earlier. And then there's the overload pickup, and it factors in this hot and cold ratio, and all of that to get the thermal capacity used at the end equals 16%. So with this cool time constant of 15 minutes, 5 of those is 90 minutes. This started at a thermal capacity used of 85%, this hot-cold ratio 0.8, and the I equilibrium over overload pickup is 80%. So at the end of 90 minutes, it's going to be at this 16% thermal capacity used. And again, this is the calculation that the relay goes through to tell you what the thermal capacity used by your motor is, and it keeps track of that. your thermal capacity drops faster from a lower TCU start. So what we're trying to show here is this is the cooling time for a unit that has tripped from a fault, and this is the cooling time for a unit that is stopped from running from 85% load, for example. So they both have 30 minutes. Here, like I said, the TCU start is 100%. Here, the TCU start is 85%, and the rest of these are the same. But what, and I wish this was easier to see, but with the tripped unit, you can kind of see here it gets to 50% capacity, maybe in 20 minutes. But from a stop position, it gets to that 50% maybe in 15 minutes. It's like I said, I wish this was a little bit better example that was, more to see, easier to see the difference. But this is what affects the time that the relay will inhibit your start or your restart. So this is how the motor looks at that. So the takeaway here is that if your motor has tripped from a fault, it's going to take longer for it to cool down enough for you to restart the motor. Whereas if you're cooling from just stopped from a running condition, it will cool a little faster and you can restart a little sooner. Both of these take the same 5 times 30 minutes to get to 0 thermal capacity, but the steepness of the curve here is a little different. So some of the other protections that we look at, these I guess are more electrical here. We're under over voltage protection. The over voltage condition, it affects the decrease in load current, can cause poor power factor. The motor flux saturation. The older motors had a more robust design. They were designed and built to run and last forever. But newer motors are designed very close to the saturation point. There's just the bare minimum of core materials in there to operate where they're designed. So any sort of over voltage or an increasing volts per hertz is going to, that over voltage will lead to saturation. That leads to motor heating. So we set our over voltage to 110% of the nameplate unless it is otherwise stated in the data sheet. Under voltage protection, your under voltage condition affects increase in current and motor heating, reduction in overall motor performance. The under voltage protection is backup protection for thermal overload element. For some cases, it will trip motor faster than a thermal overload. We set the under voltage to 90% of nameplate unless the manufacturer advises otherwise. And you put a delay on the under voltage to account for motor starts on your same bus. A motor starting on your bus is going to dip your voltage. You want, that's a normal condition. You don't want to trip off your other motors just because you're starting, a new motor. So you want to make sure there's enough delay in there. Harmonics, the measurement of harmonics and total harmonic distortion is something now that the 869 relay can do for you. The harmonics do contribute to heating, and the IEEE has made recommendations on limits for voltage distortion at 3% on any one harmonic and 5% total harmonic distortion. Given the so the relay has a 128 samples per cycle sample rate, and by virtue of that, we can get these harmonics. The 869 will measure harmonics up to the 25th order. So so that allows you to measure your total harmonic distortion, measure your different different harmonics individually, and to set limits and to alarm or even trip for those if you wanted to. The 869 also is also looking at no, that's what I just said. The voltage harmonics are the 2nd through the 25th, and it gets the total harmonic distortion. And then here, the presence of harmonic content can show problems either with transformer inrush or overexcitation, and excessive total harmonic distortion leads to heating. You can measure these and use them for monitoring or alarming, or in the case of well, I'm not sure you would use this on a motor. It's for transformer inrush. Usually we use this on a transformer relay, but that second harmonic blocking is typical on transformers. The 5th harmonic to check for overexcitation, that could be used as an alarm here on a motor. But this function, this information is available in the 869 relay. Next, we have unbalanced protection. It's your ANSI 46. And this is current-based unbalance. This is looking at negative sequence current. Unbalanced current stresses the motor, raises the temperature. It's unequal line voltage will lead to unbalanced currents. So it's looking again for things like unbalanced supply based on blown fuses or single phasing. Other current unbalance causes can be loose or bad connections, an incorrect phase sequence connection, or even stator turn-to-turn faults. We also want to look at ground fault protection. The ground fault creates a path for current from one phase directly to neutral and bypasses the load. Damaged phase conductors, the insulation on phase conductors is what a ground fault looks like. It causes voltage stress. It's caused by voltage stress, moisture, mechanical faults. So an impedance will limit your ground fault current, either a resistor or grounding transformer, which is placed between the supply neutral and the ground. So in these drawings here, it's showing your 3 windings of your motor and then a grounded neutral, or a resistor grounded neutral, or a impedance grounded. And so this resistor or impedance will limit the amount of fault current for a ground fault. You need to match up your sensing so that you can see that amount of current, but the lower current will limit the amount of damage that you get from running that or from seeing that fault. And there are some options on picking up your ground current. The first we have is to measure the actual current in the ground, in the grounded neutral. Just have a dedicated CT for that. Another method is to use the zero sequence CT. This is one CT that wraps around all 3 phase conductors. This gives you a very sensitive method of measurement. Since it's one CT, you're not worried about different CTs having different performance characteristics, and so this can be set to be very sensitive. And then the residual connection, and actually what this is doing, it's not measuring the residual. In this example, it is the relay is calculating the residual from A, B, and C phase currents. If you sum these together vectorally, you'll get your neutral current, and it can you can use that for your phase to ground current protection. Like I said, with the zero sequence CT, you don't have the issue of having to worry about CT performance. In this situation, if these CTs have a little different performance, it's going to affect that derived neutral current, and so it has to be set a little higher to compensate for those errors. So I've already talked about these without waiting for the specific slide, but again, the zero sequence CT, one CT, all phase conductors pass through that CT window. Normally the phase current summed to 0, and if there's a ground fault, you get current flowing into the motor relay. This is the most sensitive method, and it has inherent noise immunity. And this is your residual ground fault again. It's when you can't run all your conductors through a zero sequence CT. It's less sensitive because the CTs perform differently. You can end up with a false residual current, and you might even have CT saturation during starting, which is at 6 times full load amps. So you have to set your elements to disregard CT errors and use that to trip for a ground fault. Current can be measured or calculated, and again, this is showing a connection where we only have IA, IB, and IC connected to the relay, but you could, from a connection here, derive this neutral current and run it through the relay as well to get you an actual measured residual current. So moving from the ground current to a differential current now, what we're doing here, the differential summation is looking at the current into the motor is equal to the current coming through the neutral of the motor. So if you look at this connection here, we've got 3 phases. Each phase goes into the motor and comes out, and then they are tied together at this neutral point. So A current going in should match A current coming out. Same for B and same for C. So like most differential protection schemes, it can be set up to respond very quickly and will limit your damage. But the core balance method here is using 3 sets of core balance CTs. So it's similar to that zero sequence CT, where it's one CT, it's measuring the current in and the current out, should sum to 0, and if it does, everything is good. And again, this core balance CT method is can be set very sensitively and very securely. Other ways to do this differential summation is with 6 CTs, and this is let's see, this is 6 CTs used specifically for for this differential, because they are summed outside of the relay, right? C phase polarity on both C phases goes into the relay, the neutral comes out, and they're all tied together. And the same for A phase, B phase. So with this, you're using 6 CTs. They would be, should be all the same type, same ratio, but they always have a little bit different performance. So, and especially on motor starting, where you've got phase current, coming in. Well, even on the neutral side here, it's the individual phases coming out. So I guess what they're thinking is here, this motor starting is the highest current, so there's going to have, slightly different performance. But there, you set up the motor relay then to look for a differential current from the subtraction or the combination of these two. Another way to do a biased differential protection with 6 CTs is to bring each CT individually into the relay, and the 869 can accomplish this as well. It will use these phase CTs for motor protection as well as the differential protection, and then it has another set of CTs, and these can be sized differently because these are going to capture full line current. The neutral CTs, well, they got to carry line current too. I need to look at this slide some more, but it can be set very sensitive. The motor relay will calculate the difference. It can take into account different CT ratios, like I said, and again, any sort of a differential can be set, fairly sensitive. It ends up being very, very secure and good to have. So the dual slope differential characteristic that we use has 2 slopes. There's a slope 1 and a slope 2. Slope 1 is usually lower. It's used for the area of the fault where you might have, where you will have your CTs operating without saturation. They operate more in an ideal configuration. And then slope 2 is used when you absolutely know that one of your CTs, some of your CTs will saturate, so you need a little bit more margin up there in that range, and that's what that's for. The other thing we use in the differential is to look at this directional element. If all of your currents are in the same direction, that is no greater than 90 degrees apart, that's an indication of an internal fault, right? All the current is flowing into the motor. If you have an external fault, one or more of these current sources are going to be greater than 90 degrees from the rest. That gives you your direction of 0, sets that direction flag to 0, and we use that in this algorithm here. If the restraint current is small, you're operating in this this lower region, and your direction is on. That is right. Internal fault. All the fault currents are within 90 degrees of each other. So low fault current direction is set. Get both of those, it's going to trip for your percent differential. If you have an external fault that is going to turn your direction off, then you need to wait for saturation. So an external fault with saturation is going to, first it's going to shoot up here into the high restraint current area. It takes a little while for the CTs to saturate, but eventually they move up here into the trip range, because this so the saturation flag gets set. Well, no, let's see. This saturation is going to turn off, give you a 1 here, along with this high differential current, and that is going to cause your percent differential to operate. So it recognizes that that swing from the restraint to the operate region, and it will cause it to operate. Short circuit protection for large overcurrent faults is another protection we put in there. We're looking at, you want to set it above your motor starting current, and that motor starting current can also have a asymmetrical component up to 1.7 times the RMS starting current. So you set your short circuit pickup to be at least 1.7 times the maximum expected symmetrical starting current. The circuit breaker or your contactor must have sufficient interrupting capacity, or you will need to get an upstream protective device to interrupt the fault current. The caution here is, if you're using a contactor, contactors typically are fine for starting and stopping your motor, but they don't provide enough interrupting capability. So it's hard for them to interrupt a full fault current. So you may have to trip an upstream breaker for a short circuit fault. I talked earlier about RTD biasing, but this is a little different. The stator RTD temperature alarm or trip can protect the winding insulation. What we're doing here is we're using the same RTDs that are embedded in the stator monitoring temperature, but you can actually set a stator RTD trip level, and you set it at or below the maximum temperature rating of your insulation. For example, here, motor class F insulation, the temperature rating is 155 degrees. You set your stator trip RTD to 145. That's 155 minus 10 degrees as margin, and so you can use that value to cause a trip. Or you can, and then you can set a stator RTD alarm before that to get a warning that your temperature is rising. Okay, starting control, what we mean by that is the is your acceleration protection. It looks for abnormal conditions. This is showing starting with a fan brake engaged or sudden starting with a load increase. It adapts to the time and current from the last 5 starts. You want to avoid nuisance tripping when the system voltage is suppressed or various loads during acceleration. So it's set greater than the maximum start time. So you've got your motor acceleration time, your full load amps, and you're allowed to have this acceleration current for a certain amount of time, and then it should drop off, or you want to trip, and it's detecting, you know, either a jam or something stalled in the motor. Okay, so the thermal capacity used is also used to control motor starting. It's we call a start inhibit for a hot motor. So the relay allows a start if the available thermal capacity is less than required for less than the required thermal capacity needed for starting. If your start inhibit is not used, then you must, if the start inhibit is not used, then you must wait until the TCU falls below 15% to restart the motor. So if you don't set this up, the start inhibit is going to just use this nominal 15%. But by setting up these factors, you can maybe it can maybe allow you to start your motor a little sooner because it knows that it only needs a certain amount of capacity to be able to start. Here, let me show you an example. So calculate the thermal capacity required to start, and this is based, like I said, on the last 5 starts. And for the thermal capacity used for these last 5 starts in this example are 24, 23, 27, 25, and 21%. So the learned starting thermal capacity used is 27%. That's the average. And then we have this setting of 25%, this thermal capacity used margin, 25%. So the motor or the relay is holding on to this 33.75% thermal capacity used value as the capacity that the motor needs to restart. So if your thermal capacity used is above, if it's above 66%, if it's 80%, something above 66.25%. If it's above that, the relay is not going to let you start your motor. It's got to drop down to the 66% for the relay to allow starting. So if your motor had been running in an overload condition and the thermal capacity is some value, your example is 80%, you're not going to be allowed to restart. When the motor cools, it falls to 66%, which gives you then enough thermal capacity to restart your motor. We also have settings for starts per hour and time between starts. These are usually provided by the motor manufacturer, and so it's just values that you can set in the relay. The relay will inhibit starting based on the just the clock time from when it was stopped. Okay, so I want to talk a little bit about variable frequency drives and cyclic loading filtering. And this was a question I think that Eduardo got in the email advanced questions. So there's some options for your VFD protection. You can set your VFD protection on your source side, and in this case, then we're going to look at your phase over current, your neutral over current, as well as a ground over current going into the VFD. You can also set it up for load side motor protection, and this will get you your 46, 49, 87. This is your imbalance, your thermal protection, your differential protection. Again, this thermal protection, differential protection is very important for protecting the life of the motor. So it can be set up on the load side of the VFD and protected that way, or you can set up an integrated protection scheme, kind of a hybrid. It uses the source side and the motor side connections, and it just sort of looks at whether the VFD is operating or not, and uses that to enable or disable some of these functions. But the 8 series of relays will track down to 3 Hertz. Their tracking range is good from 3 to 72 Hertz. So all protection functions, any sort of tripping or alarming will still operate correctly in these in this expanded range. This is just an example of the settings. The frequency tracking can be set for tracking from voltage or current. The relay samples on the motor load filter interval. The VFD mode drives all motor current functions except short circuit, ground fault, and differential. There is blocking based on the frequency range of the thermal model and being voltage dependent. And then with the VFD not bypassed, you can use that to block the voltage elements. If the bypass switch is closed, then your VFD functions are disabled and the frequency tracking switches back from currents to voltages. Then all your motor functions then are using the normal RMS current. So there's a setting in here that tells whether it's bypassed or not. That's it up here. This motor load filtering is a little different. This has more to do with the with cyclic loading. Think like a reciprocating compressor that, part of the stroke it is fully loaded because it's compressing, but then on the return stroke it's not loaded as much. That gives you input motor currents that have this cycling effect, and what we do then is we filter these, and basically you select a value that will smooth out this curve. And what it does is takes several of these cycles together to give you a smoother looking curve, as opposed to, trying to sample when it's fully loaded and sample then when it's lightly loaded and back and forth. So that's just another setting, another feature in the relay. So I feel like I'm running out of time, so I'm going to try to go through these a little quickly. But this was the question, why can't I start my motor? And the answer, the inhibit is set too high. So in this example, we're showing the thermal capacity used during a start. So when it starts, it runs up to 85%. It has a cool time constant of 15 minutes, and it takes a certain amount of time when it's running to get to the equilibrium point. But if it stops from a fault, it has a slightly different curve. Here's the inhibit example. So we calculate the thermal capacity required to start, and we did this calculation earlier. Yeah, so this is looking for the TCU to fall below 66%. Yeah, we saw those slides. Here's the story. The facility had a high inertia load with a learned thermal capacity used at start of 78%. The start inhibit margin was set at 25%. So the thermal capacity used has to fall to this formula, which calculates out to 2.5%. So it's got to be almost down to 0 thermal capacity used before the start is allowed. A less aggressive set, and keep in mind this 25% is margin, right? So it's already at a safe value. If you use a less aggressive setting of 5%, this would allow it to restart at 18%, and be easier to hit. So that right, the time between 18% and 2% is another hour added to that time. So that's a little rough. So lessons learned, your start inhibit needs to match the application. Enabling start inhibit is not real helpful for high inertia motors. If the motor start thermal capacity used is a reasonable level, less than 60%, then we always recommend to enable the start inhibit, but use a reasonable thermal capacity use margin setting to prevent unnecessary start inhibit blocks. Here's another case study of what can go wrong, and this is using the cooling time constant as the cooling time. So the facility found cooling times of 60 minutes cold and 125 minutes hot. They set these times as the cooling time constants in the motor relay. Of course, this setting really doesn't affect anything. It lays dormant for several years until a trip occurs. So the learned start is 66%. The thermal capacity used margin is 15%. So you've got 100 minus 66 times the 1.15. You've got a 24% that the thermal capacity used has to drop to be able to start. But with the cooling time constant set at 125 it takes 178 minutes to cool down to 24%. If they use the correct cooling time constant of 25 minutes, it takes only 35 minutes to start after a trip. So it's a substantial difference. And remember that remember that the cooling time constant is not the same as the cooling time. So the stop cooling time is considered, after it trips, after the motor stops. It's the time for the motor to go from maximum insulation rating to ambient. So from 100% thermal capacity used to 0% thermal capacity used. The stop cooling time constant is the cooling time divided by 5. So they use the cooling time, not the cooling time constant. So it was 5 times the value that it should have been. The relay will only accepts a cooling time constant, but confusing these two leads to excessively long lockout times. General rules: if your motor is rated for 3 cold and 2 hot starts per hour, you should not have a cooling time constant greater than 30 minutes. And you should be suspicious of any cooling time constant greater than 60 minutes. Okay, I'm gonna keep going with these case studies because they, I think they're helpful. I can't hear if anybody's giving any questions or feedback, so I'm just going to keep going. In this case, the customer erroneously set the hot-cold ratio to 13%. Setting should have been 87%. And where this confusion came in was that you've got this hot-cold ratio, but there's also a 1 minus that ratio in there. So what they had done was taking this at 13%, where it should have been I guess 1 minus 13 or 87%. Just taking the wrong ratio there, basically. But RTD biasing was applied and the motor would not start. So why was that? So the RTD biasing looks like this. And you've got your maximum, your middle, and your minimum. And this middle is set by the by that hot-cold ratio. The correct way to do it, see this, they had this hot-cold ratio 0.13, and what that gave you was at 55 degrees, the stator had a thermal capacity used of 20%. Right? Oops. Sorry. 55 degrees, 20%. So that was driving your thermal capacity used up very high. If you look at the correct calculation at 55%, it would have only been 3%, so a start would have been okay. So that was a lesson learned there. Let's see. I'm gonna move along a little bit here. Let's take a look at this these other blocking elements. So if I have a motor relay and I'm using the thermal model, are these other inhibits really necessary? And the answer there is a yes. These starts per hour, time between starts, restart, delay, lockout, these are all they're manufacturer recommendations, but they are not just there for as suggestions. It may also affect your warranty on your motor, so it's a good idea to include those. So some final thoughts on motor lockout and other blocking inhibits. If your inhibit margin is set too high, that can prevent timely motor restart. Cooling time and cooling time constant are not the same thing. Relay uses the cooling time constant. Hot-cold safe stall time affects the motor steady state. Thermal capacity used, which affects the motor thermal model and inhibit restart. High inertial loads use large thermal capacity during the start. These need significant cooling times after a trip. And the starts per hour, restart rate, time between starts might be redundant, but probably is necessary for your warranty. Okay. I know we've got question and answers period set up towards the end, and I hope to honor that. I am moving now away from the motor protection overview and looking specifically at the 869 motor protection relay. So we'll look at some of the features here as they pertain specifically to the 8 series relay and the 869 motor protection relay. So the 8 series family of relays, we have designed it so that we don't have any electrolytic capacitors. Electrolytic capacitors were the capacitors that, as they aged, they would dry out. This would cause them to fail if they were powered down and then subsequently powered back up. So that was a failure point in our relays that we have eliminated here in the 8 series. The front panel of the 8 series relays are IP54 rated, so dust protected against splashing water. Conformal coating is now standard. In our previous SR relays, the conformal coating was optional. If I was in the same room with you, I could show you the relay. When we draw it out of the case, it has a extruded aluminum inner case that is very sturdy, so it adds to the just the robustness of the design. We also include an environmental monitor inside the relay. This is looking like for things like excessive temperature, high humidity, high ambient temperature and humidity. It is also monitoring surges on the power supply to see if there's any problem with the control power, that any of these things might lead to a shorter life on your relay. And you can even alarm for these things to know that, hey, I'm putting this relay under some stress. I may need to replace it earlier than I expect to. We've also used the IPC Class 3 manufacturing standard. This is this has to do with circuit board assembly, and especially has to do with soldering, the amount of soldering or solder that gets put into the circuit board. This is basically an automotive class of manufacturing. Some of the hardware features on the 8 series, the draw out design. Each of these relays can be, there's one set screw you can remove that and then pull the relay out of the case. Relay features a color display. You can do things like display a single line or display your voltage and current phasors on the front of the relay. We offer an option for arc flash detection. We have also field removable power supplies. This is the sort of the exploded view of the relay, showing the front display and the extrude aluminum case and circuit boards. The magnetics remain usually inside of the case. They can be removed, but this keeps you from interrupting your current circuits if you draw out the relay. And then I spoke about the power supply. It is field replaceable. So as you know, we've removed the electrolytic capacitors, but we've also made it real easy to replace in the field. If your capacitor fails, you just draw out the relay, loosen one screw, and you can replace that power supply. Some specifics about the 869. This is the list of all the ANSI device numbers, and it has a it has the different protection elements that are specific to motors. It also has over under voltage, over under frequency, all of your instantaneous and time over currents, including directional elements. There is there's the list. I think you'll find everything you're looking for. The 87S, the differential is set up to where you can do that with the phase CTs and neutral CTs, or you can do it based on your core balance CT. Just some options there. So next I want to show you all the software and how it connects to the relay. So first I want to show you the no, that's not it. This is it. The Launchpad software. This is our EnerVista Launchpad, and you can use this software to basically launch your different setup software. It also will maintain copies of manuals and brochures. It also keeps them up to date. It will go out and check with the GE server and will notify you, and can even automatically update any manuals that have revisions to them. This is also where we keep firmware files, setup utilities, setup programs, that sort of thing. But you can also install the setup software and just run it directly from your from your desktop. Now I've closed this. Here we go. And I wanted to show you where I start the setup software from. So this is going to act all squirrely. All right, so I'm just going to close that. Just give me a second. we'll get that out of the way. We'll take a look here. All right, so this is the, I already had the software open and ready to go. So I wanted to show you a few things here. The first thing you want to do when you're going to connect to a relay is you may need to configure this quick connection. Here I'm just going to use this USB, the slave address and the port. They come in pre-configured. If the actual value in your relay is different, has been changed, then you would have to adjust that address. This port 502 is pretty standard. But from here I can just hit connect, and it will go out and connect to this relay that I have right here. And then it will put the it will show the relay then on the in this online window. And from here I can go in and look at different things. I can look at the quick connect device, and I can read device settings. If I do a read, it will save it then to my offline window. I can compare it with another setting file. And then if I've saved it down below, I have my my offline options here, where I can write a settings file to the device. I can also compare files with defaults, compare two setting files. I have the ability to create new files based on particular order code and firmware. I can duplicate settings files, move them from site to site. These sites here give me another way to organize all the files. The main thing I want to show you here is this service report. This last button on this row, this last icon, it will go out and connect to this quick connect device and generate a service report. A service report contains all of the pertinent files from the relay that that technical support or your application engineer will need to be able to look at an operation and diagnose if it was a correct operation, or if it's a setting problem, or just what have you. So, and I know this is the operation folks' biggest fear. It's an engineer with a wrench, but there you have it. That's how you get the service report. It creates a zip file that you can just email to us, and that. I want to jump in and show you the quick setup. No, not status. Quick setup with the 869 relay. Here we go. It gives you this 2-page form basically to fill out, and it just has some some basic settings. Your CT, your motor full load amps, some other factors, things like that, and then protection elements. And from here you can configure thermal model, different these different protection functions. They're all on one page. This is if you need a quick way to configure your relay. Say you have a spare relay on the shelf, it's not programmed. This will allow you to put it into the draw-out case, and configure it specifically for the motor you need to protect. You know, get these basic protection settings into the relay and get the motor back in operation. So that's handy. The other thing I want to show you, if we've got a little bit of time here, is the under set points we have this protection summary. So everything, all of the settings that are available in the relay are shown in the protection summary. And this just takes a minute or two to pop up. And from here, you can look at all 6 setting groups. You can look at all your I/O cards. If you have, you know, something in G or H, you can look at those. And you can look at all the settings, or you can look at just the enabled settings. So I've only got a few elements set up here in this this particular relay. But from here, I can see what is set up. I can see that, for example, this thermal model is set to trip. If I click on the trip button here, it takes me straight to the settings, and I can edit those, or just, you know, just reference them if I need to. So that's helpful. And if I want to, you know, just change settings directly, I can go in here under, for example, voltage. If there is a, maybe there's a phase under voltage that I want to set, so I could go in here and enable that to trip. I'd be looking at a phase to phase or a phase to ground voltage. I set it for a certain pickup and a minimum voltage. That way, if it, so in this, for example, if I set this to 70%, if it drops below, this is under voltage, drops below 70%, it's going to pick up. If it goes down to 0 or goes below 20%, it's going to drop out. So this will detect a low voltage, but it will not detect a 0 voltage condition. And it has the it has some logic here for, you know, do you want this to trip for any one phase, any 2 phases, or you have to have all 3? There are some timers in here. All of the settings have a, all the functions usually have a block. This can be used to block that function. You can set it up to operate other auxiliary relays in addition to the trip contact here. And then we can capture events or targets based on the settings here. So Eduardo, I think I have covered everything I was supposed to, and I think I've left about 15 minutes for wrap up and any questions and answers that we want to address. So I will stop talking for a minute and ask Chris if he has any questions we need to address, or if whatever we need to do.
Okay, Paul, thank you very much for the presentation. I did get another question via email. It's does the A69 has a reset button, a restart, emergency restart button?
Yes, it has that function. It is not like our previous relays where you had to short out a contact. It can be like that, but it can it's also configurable. It can be configured for a contact input. You can configure an input from the display. You can even do it over communications. But you have to add that function. Typically, it's not wired out or configured, but it can be. So yeah.
Christine, I don't know if you got any more questions, but that's all I have on my queue.
I don't think we have any unanswered questions in the Q&A so far.
Was there anything interesting that that might benefit the entire group?
We didn't get too many questions today.
Okay.
Our audience is a little bit shy. If you guys have anything, feel free to pitch it in the Q&A box and we can talk about it.
Well, Eduardo, I would suggest that we give these guys 10 minutes of their time back to them and thank everybody for their participation. And if there are, if you have future questions or something else comes up after the presentation here, you can certainly get in touch with us through your normal GE contact channels. Sound good, Eduardo?
Sounds good, Paul. Thank you so much for your time for the presentation. Christine, you as well. And thank you everyone for participating in today's event. As I stated before, this session was recorded and the video will be available to you for the next 90 days or so. Just use the same link that you will use today to access this event, and the recording will be there. We'll be sending the presentation tomorrow, and if you need the certificate, please get in contact with me, email me, and I'll make sure to get it out to you within the next 24, 48 hours. With that said, I don't see any other questions. Well, I think there's one question that came in here. Christine, do you see it?
Yeah, I see a question about what's the cost difference between the single neutral CT versus, say, the CT setup for ground fault protection. I don't know, Eduardo, if you're familiar with CT pricing. I know on the PNC side, Paul and I don't necessarily deal with CT pricing, but potentially it could be pretty significant, I would think, one CT compared to 6.
Yeah, I don't handle any CT pricing either, so I guess you know, yeah, it could be because you're talking about 6 versus 3. So yeah, sorry, I don't have any reference price on the CT that I could use to help you out. So if there are no more questions, then thank you everyone for participating, and we'll be sending you all the presentation. Have a great afternoon and stay safe.